In this paper, we have explored safe multi-agent satellite servicing. In particular, we have explored this scenario where we have a tumbling RSO and a bunch of modular servicing agents which wants to relocate from one point to another point in body while the body is still tumbling. And in this process, they have to avoid hitting each other as well as avoid hitting the RSO. So as a first step, we want to just give a background on how this fits in a larger application of modular satellite servicing. So the application that we are targeting consists of a mothership and Bernese CubeSat servicer modules. We call them T-pods. The mothership approaches the RSO. First, it analyzes the tumbling motion of the RSO using 3D computer vision techniques. And once it is confident about the tumbling rate of the RSO, it will start deploying these modular agents towards the RSO. Now, at the end of this activity, what will end up is there are a bunch of teapots at the center of the RSO. But to get a better leverage arm, we want to kind of move towards the end of the RSO. And that's where the relocation part comes in. Since there are a bunch of teapots operating in the vicinity, if we don't care about the collision avoidance, there are chances that the teapots will collide with each other. As well as since the RSO is tumbling, it is also possible that these teapots will collide with the RSO. So first of all, we wanted to generate some reference trajectories for these teapots, and that is done using indirect optimal control. The basic idea is the keep out constraint of the RSO is formulated as an ellipsoidal QOC, and then it is added as an augmented state. The indirect optimal control problem is formulated and then solved using forward shifting algorithm. So the reference trajectories are picked such that in a normal case where there are no additional actions, the teapots will collide with each other. So the trajectories they pass through each other in space and time. So if the teapots just follow these reference trajectories, there will be collision between teapots to teapots and then teapots to RSO as well. The second step is to have pose information of the teapots, and then the idea is basically have a relative localization of teapots with respect to the mothership. And for that, we are using relative ranging, IMU, and monocular vision sensors. Our translational and rotational dynamics are coupled due to this offset between the UWB sensor and the center of mass of the bodies. The filter formulation is multiplicative extended Kalman filter. It tracks the position and velocity of the UWB receiver as well as the attitude error of the module. Whenever we have the IMU update, we propagate this attitude error. And then whenever we have the range update, we incorporate this information to produce position and velocity estimates. And finally, we perform the quaternion reset where we update our reference quaternion using the attitude error that we accumulated, and then we reset it to 0. And this filter formulation is experimentally validated and analyzed thoroughly in our earlier publications. You can find more information about this in referred publication. The next is to perform guidance and control. For that, we have considered receding horizon discrete linear MPC. Here, the whole idea is to formulate a cost function which penalizes the deviation from a reference trajectory. And then we can perform this operation over a prescribed control horizon. Also, we have to use the recursion between the future state as well as the current state and the control history to replace the states with the control history. And what we will end up by this replacement is a quadratic program which just depends on the control history as the decision variables. And then we can add the control saturation constraint as well as state inequality constraints on top of that. The next step is to perform collision detection and avoidance. The first modality that we considered for the collision detection is using the shape of these objects. So the whole idea is to inflate the convex hull of this object with the same inflation factor. At some point, they will touch each other. And at this intersection point, if my inflation factor is greater than 1, I will say that there is no collision. And mathematically, this can be achieved using first finding A and B for all the points which lie on this convex hull, and then formulating an optimization program which basically try to minimize this inflation factor with a constraint that this point lies on both the convex hulls. And this algorithm is robust enough for any complex shapes. So for example, if we have this kind of RSO, if we inflate again its convex hull and then find the intersection point, we will be able to determine the collision between teapots and the RSO. Once we have the collision detection, the next step is to perform the collision avoidance maneuver. For this, we have multiple options. For example, we can try to move the target, but usually that is not feasible. And then we are assuming that we will not be changing the attitude of the chaser to avoid the collision. So that leaves us with only one option, that we have to move the chaser to avoid the collision. And this can be achieved by solving this additional quadratic program where the objective is find the du such that whatever the inflation factor that we had previously, now it is being modified by this additional divergent du, and then the combination of this previous inflation factor and the modification should be greater than the threshold that we have set. So now the only unknown in this framework is this partial derivative of the inflation factor with respect to the chaser position. And then it turns out that this is the byproduct of our original linear program. So the original linear program that we have formulated to find the inflation factor, if we consider the dual of this program, what we end up is a Lagrangian of this function. And then the gradient can be simply computed using the dual of this variable. To show the effectiveness of this approach, we have considered a planar simulation scenario where if there are no collision avoidance maneuvers, the teapots will collide with each other. On the right side, we saw the simulation with the collision avoidance. And initially, the teapots will follow the reference trajectory, but at some point, they will be able to detect the collision in future. And then first, they will try to negate this reference velocity that they have. And then they will try to find a safe passage through which they can reach to the original reference trajectories. However, it is important to know that there is a lot of back and forth. There is a lot of chattering of these control inputs. And this is also visible from the history of the control inputs. So in summary, we can do collision avoidance using polytopic hulls, but it is not very efficient. Now, one can argue that simply we can have some kind of phasing maneuvers to avoid the collision. For example, we can just wait before starting the motion of the second teapots. Usually, this kind of phasing works when we have less number of agents, but it is not very scalable. Now we have applied this collision avoidance approach for a full 3D scenario. Again, we have the KOC with the ellipsoidal constraint, and then we have a reference trajectory where there are possibilities of collision with the RSO. So with this framework, you can see the initial deviation to maintain the separation distance. After that, it follows the reference trajectory, and then at some point, again, there is a deviation to maintain the inflation factor. Now, some interesting phenomena happens when we apply this framework to multi-teapot scenario. So again, there is an initial deviation to maintain a separation distance with the RSO. But when they are trying to go back to their original reference trajectories, you can see that they go into this deadlock situation. The orange teapot is not able to find a safe passage to its reference trajectory. And then when finally it is able to find a safe passage, its original trajectory does not look at all like the reference trajectory. So what we can conclude is this kind of approaches are great in avoiding stationary objects, but this kind of approaches are not very well for avoiding any head-on collisions. And that's why we need some fundamental approaches like control barrier functions, which David is going to talk about next.
Thanks, Deep. So, as you mentioned, we wanted to try another approach to collision avoidance. And so for this, we used a very common technique in the safety critical control literature known as control barrier functions. So in using control barrier functions, we generally say that safety is described as some subset of the total state space, where safety is described by some function that we design h. And we say that the safe set is all states where h is positive. So there's various ways to define this, but this is kind of the typical way. So the condition for forward invariance or safety of our system is nothing but the total derivative of h being positive everywhere along the boundary of the safe set. So if we consider a nonlinear control-affine dynamical system in this form, which is a form that many dynamical systems take, then we can expand this necessary and sufficient condition for invariance and therefore for safety. And we find that because of this control affinity in the system, the constraint is actually linear in the control. And so this is really nice because now we can take any control signal, this U desired, and filter it very quickly with a quadratic program, for example, because we've basically converted our state constraints that we designed into convex control constraints because of that affinity. And so this U desired, this control signal, could be anything. So in our case, it could be the MPC output, for example. And so we solve this optimization problem where we try to get as close as possible to the desired signal whilst adhering to these convex control constraints, which will guarantee safety of the system. So we have here the example of the planar collision avoidance that we saw before, except now instead of using the decol approach, we use the CBF approach. And we can see on the right-hand side that the CBF approach it avoids that deadlock that we saw with the decall approach. We also compared the computation time required for the decall approach versus the CBF approach. And unsurprisingly, due to the form of the CBF, we see that in this table here, the CBF approach is much faster than the decall approach. Having seen the effectiveness of the CBFs in enforcing the planar constraints, we now move on to the 3D constraints. So in the following cases, we will over-approximate each agent as a sphere with a certain radius, and we describe the T-pods to RSO collision constraint in the RSO body frame as this H keep-out zone, where, as before, we'd like to make sure that H is always positive to ensure safety of the T-pods. And we also define a T-pods to T-pods collision avoidance constraint, which is, again, in the RSO body frame, except now the H function that we describe takes in each unique pair of T-pods, and we develop the same kind of form of the constraint where we're keeping this H positive, but now we have this concatenated state that we have to keep track of. So standard CBFs often assume perfect state information, but obviously, as Deep mentioned earlier, we can only use reconstructions of our state via the multiplicative extended Kalman filter. So we wanted to basically address this kind of uncertainty by considering an additional buffer per agent. So we have this eta term, which is proportional to the covariance in the position space, and we modify the constraints according to this uncertainty buffer. So essentially, you can think of it as increasing the radius of the sphere by this buffer amount, and we simply just have to modify the constraints that we saw earlier with this extra eta term per agent. So we just saw that the 2D planar case worked really well with the CBFs over the decall approach, but we found that when enforcing only the 3D constraints for the T-pods to RSO collision avoidance, the CBF constraint overreacts significantly more than the decall approach in trying to avoid safety. And while this is something that could be tuned, we wanted to use the best of both worlds. So we used a hybrid safe control solution where if there was a T-pods to T-pods collision, we used the CBF solution, and otherwise, for only T-pods to RSO collisions, we use the decall approach. So here we have an example of the hybrid approach in action, where the two agents are trying to relocate on the tumbling RSO, and we can see that the CBF effectively takes care of the collision avoidance and also avoids the deadlock that we saw earlier with the decall approach, all using only reconstructions of the state with the estimator. And now the agents are able to go back on their reference trajectories, and the decall approach kicks in right at the end in order to avoid the collision with the tumbling RSO. So we performed a 500 trial Monte Carlo analysis using the hybrid approach that I just mentioned and estimated states using only reconstructions from the estimator. And we found that over the 500 trials, 97.6% of the trials were collision-free. As you can see, there's very few cases where this blue dotted line goes below this red safety line. And so we can see that the hybrid approach with our buffer based on the covariance worked quite well, as we had hoped. So in conclusion, we developed a safe, scalable, closed-loop GN&C solution for multi-agent relocation on a tumbling RSO, which is adaptable for any convex hull of T-pod or RSO shape due to the decall approach, and was shown to be computationally tractable and very effective at ensuring safety. So thanks for listening.